Howdy. In our earlier lesson, we talked about work and how to compute work. And I want to talk a little bit now about why physicists care about the amount of work that's done. So I want to consider an equation of motion that you know and love. V squared equals V0 squared plus 2a times delta x. And what I'd like to do is to take this equation and rewrite it just a little bit here. Just like so, by subtracting V0 squared from both sides. And I would also like to talk about what it means. So we have an object that is moving in a straight line. Maybe he's moving in this way, and he experiences an acceleration and a delta x, like so. And the result is that he starts at one velocity, v0, and by the time he gets to the end, his v0 has gotten much larger because of the acceleration over that distance, delta x. Well, suppose that I take the a times delta x and I rewrite it like this. If I ask the question, here is my object with mass m, why is it accelerating? You would be able to tell me, because it's experiencing a force. And so if I have my object of mass m that is experiencing a force, then you would tell me that F is equal to m times a. Or in other words, a is equal to F over m. Now, here's where this becomes really interesting. If I take this equation 1 and this equation 2 and I put them together by substituting right here, then I get something that looks like this. V squared minus VO squared is equal to 2 times F over m delta x. And I recognize that the F and the delta x, product of F and delta x, is the work done on the object as it moves in this direction. So I can rewrite this as 2 over m times the work, or if I want to clean it up by dividing both sides by 2 over m, we're multiplying both sides by m over 2. Then these cancel out, and I get work is equal to 1/2 mass times v squared minus 1/2 mass times v0 squared. This quantity right here, 1/2 mv squared, is a basic quantity that we want to measure for objects, and we're going to call that the kinetic energy, or the energy that an object has because it is moving. We're going to give it the symbol K, and we're going to define that as 1/2 mv squared. If we use that symbol K, then K0 would be 1/2 mv0 squared, or the initial kinetic energy. And if we substitute into our equation here, 3, then we get a very nice compact explanation of what work does, and that is that work equals K minus K0 for the change in the kinetic energy of the object. This is the very famous work energy theorem. Which says that the amount of work that I do on an object will always change its kinetic energy by that amount. In other words, work adds energy, or can take away energy if it's negative work to an object. So that's that. So what does this look like in practice? Well, I want to show you a couple of examples of how we might use this. First example I want to consider is an object that is experiencing a constant force. And let's make this object be maybe a fairly heavy crate of mass 50 kilograms on a frictionless surface. In other words, mu equals 0. Now, I realize that's not physically possible, but what that does is it allows us to analyze the effects of just one single force. And now we're going to have a force of, let's give it 100 newtons at an angle of 30 degrees from the horizontal. And what I'm interested in doing is watching this crate as it slides under the influence of the force. And let's give it a distance of maybe 5 meters. So my crate is now going to slide. And if you picture it in your mind, because this crate is receiving a constant force, it is going to accelerate. It is going to get faster and faster as it goes. And so we now ask the important question, how fast is the crate going after sliding a distance of 5 meters? Now, you actually have the needed tools to answer this question using Newton's laws. So one possible analysis that we already know how to do would be to do sum of forces equals mass times acceleration, and then from there I could use an equation of motion, v squared equals v0 squared plus 2a delta x. I could do all that. It would require turning my force here into components, but I can do it. But work energy is actually preferred here because it's simpler. I'm going to use the fact that work equals delta K, and I'm going to compute the work very simply as work equals force times distance times the cosine of the angle between. And in particular, we have a force of 100 newtons applied over a distance of 5 meters, and the angle between the delta x, or the distance, d, and force is 30 degrees. On this side, the delta k is going to be equal to 1/2 mv final squared minus 1/2 mv initial squared. Now, I realize I got in a little too fast here, and I did not specify an initial velocity. So let's go back and do that. Let's assume that the crate is starting from rest. So normally a problem that's well thought through would give you that value. Okay, so I can now plug in some numbers. I know that the mass of the crate is 50 kilograms. I do not know the final speed of the crate. I do know that the initial speed of the crate is 0, so the initial kinetic energy of the crate is 0. So please notice that k equals 0 is another way of saying that an object is stopped. Now it's just a matter of plugging in numbers. 100 times 5 times the cosine of 30 is going to be, we'll pull up the calculator here and see what it is. 30. Try that again. There. 30 cosine times 500 is 433 joules worth of work done. And this is kilograms here. And so when I solve for V, go ahead and do that. Times 2, oh, there it goes again. Times 2 and divided by 50. And square root. No, that isn't what they wanted to say. They wanted to give me a square root. Where's our square root? Okay, let's try that again. 433 times 2 divided by 50 is going to be divided by 25. Is that amount, and the square root of that should be, why do I not have a square root right now? There it is going to be 4.16 meters per second. So the work energy theorem then gives us a very efficient way to avoid having to do free body diagrams followed by Newton's laws. And we like it. Physicists actually prefer to use work energy wherever they can. Let's take a look at a second example that's slightly more sophisticated. Let's imagine that we have an object with a force that is given in a graph. And let's say that the force has a maximum value of 10 newtons here, and the distance traveled is going to be 4 meters, like so. And we are given a 5 kilogram object that is subjected to this force as seen in the diagram. And as the diagram says, it travels a distance of 4 meters. And assuming that, let's make up a number, V0 is equal to 1 meter per second, what we wonder is, what is V final after 4 meters distance? Okay. So again, we're going to appeal to work energy. We're going to start with work equals delta K. And on the left-hand side, we're going to compute the work as an area. The amount of area under the curve is equal to the work done. And that area is derived from the shape of the force graph, which is a triangle. And on this side, we're going to write change in kinetic energy as 1/2 mv squared minus 1/2 mv initial squared. And it's a 5 kilogram object. And it has an initial speed of 1 meter per second. And now this is a matter of simply plugging in. On this side, we get 20 newton meters, or joules. And on this side over here, we get 2.5 v squared minus 2.5. And so solving for v, we get, did it again. We get 22.5 divided by 2.5, and that's v squared. So we take the square root and get v is equal to 3 meters per second.